Up until this point, we've discussed the basics of kinematics. That is, we've talked about distance and we've talked about displacement, we've talked about speed and velocity and acceleration. And for some people, those can be pretty difficult concepts to really try and get down deep and conceptualize. Well, the good news is we'll be talking about these motions in terms of the graphs of their motions. So in this tutorial, what I'll be doing is I'm going to briefly talk about why it is that we use motion graphs and how they can make life for us easier in physics. We're going to talk about how you can get actual numerical data from these graphs, like values for acceleration, or values for displacement, or values for velocity. And then we're going to talk about how you can represent the same motion on different graphs, like a distance versus time graph, or a velocity versus time graph. We'll also mention how change in displacement or velocity can be represented on a graph, either by the value for the slope of a graph or the area under the curve of a graph. And then we'll take a brief look at the special case of freeform. All right, so why motion graphs? Well, graphs help to arrange information or data in a way that's easier for a person to just glance at it quickly and interpret it in a visual way. And because of these graphs, you can see visually what type of relationship exists between two variables, say distance and time or velocity and time. Or you can determine if a relationship even exists at all just by looking at the data and see if they appear to be linear or appear to be parabolic. With motion graphs, you can quickly and easily determine if an object is speeding up, slowing down, changing its direction, moving with a constant speed, or if it's moving at all. For example, consider the data in the table shown below. How would you describe the motion of this object? Well, let's try to give it a shot. At time of 0 seconds, at the very beginning, it appears to have displaced itself 0, so it's at the beginning. And after 1 second, it's 3 meters away from where it started. And after 3, it's 9 meters away. And after 5 seconds, it's still 9 meters away. And after 6 seconds, it's back down to 3. And after 7, it's 0. Is it possible to just take a look at these data and try to get an idea of what's going on? Yeah, but that would take some time to mentally organize the data. And that can be either time-consuming or confusing or both. So now, let's take a look at a graph of those data on a displacement versus time graph. First of all, let's just check to see if we have everything that a graph requires, like a title, like axes titles, along with units, numbered axes, and data points for each one of our positions. And you can see that at time equals 0, 0 displacement is represented by that. After 1 second, 3 meters away is represented by that. And after 3 seconds, 9 meters. And you can see that as these data are plotted, you get a story about what's going on here. And whenever you take a look at the graph of displacement versus time, you should be asking yourself, what happens to displacement as time goes on? In other words, as time increases or goes along, what's going on with my displacement? Well, in the first 3 seconds, it appears as though I'm getting further and further and further away in a linear fashion. So yeah, there appears to be a direct and linear relationship between displacement and time for the first 3 seconds. But after, in the next 2 seconds, you can see that my displacement does not change at all. I'm still at 9. And it should be quite apparent that at this position here, the object is not moving at all. In the next 3 seconds, we see that our displacement decreases or gets closer to the origin of where we started. And as a result, as time goes on, when my displacement decreases, there appears to be an indirect and linear relationship between displacement and time. In other words, I'm heading back to where I started. For every graph that you look at, you should always be asking yourself, for each segment, as time goes on, what happens to your y-axis? Whatever is on your y-axis. In this case, in particular, it's displacement. So as time goes on, what happens to my displacement? And then you should ask yourself, what does this indicate about the motion of the object? Is it moving? Is it getting further away? Is it going back toward where it started? Is it moving at a constant speed? Is it speeding up? These are questions that you should be asking for every graph that you analyze. In physics, we will be using graphs in one of two ways, either by just trying to get a qualitative idea about what's going on with the motion of an object, or we can try to obtain numerical data from these graphs by looking for things like displacement and distance, or speed and velocity, or the acceleration of an object, By looking at the data as they're plotted on that graph, you can make calculations or find actual values for these quantities. For example, in the last graph we viewed, displacement was increasing from 0 to 3 seconds. It did not change at all from 3 to 5 seconds, and then it decreased from 5 to 7 seconds. How far did the object move during each interval? In other words, what is the displacement of the object during each interval? To get that information, you need to only take a look at the y-axis. You can see that from 0 to 3 seconds, the object has been displaced from 0 to 9 meters. So for this first interval, it's 9 meters. And for the next interval, from 3 to 5 seconds, it has been displaced 0 meters because it's still at 9 meters for every second. From 5 seconds to 6 seconds, in 1 second, it has been displaced from 9 to 3 meters for a total of 6 meters. And then in that last second, it goes from 3 meters to 0 meters for a total of 3 meters in the opposite direction. So we go 9 meters away, and then we get 9 meters back to end exactly where we started. When we're asked what is the speed of the object during each one of these intervals, well, that information isn't necessarily as apparent, but it's still possible for us to determine that by using the information from the graph. As we've seen in labs that we've done up until this point, it turns out that the slope of the graph has a significance. It represents something. What is that something? Well, for a distance versus time graph, the slope of the graph represents the velocity of the object. Remember that slope is equal to the change in your y variable divided by the change in your x variable, or y2 minus y1 divided by x2 minus x1. On this graph, our y value is displacement and our x value is time. So when you determine the slope of this, it is change in y over change in x, which is the change in your displacement or distance in this case, divided by the time, which is d divided by t, velocity. So if you would like to determine the velocity during each interval, then you need to simply find the slope of the object during each interval. For this graph, the speed of the object from 0 to 3 seconds can be determined by finding the slope of the line that's made on the graph between that time period. In this case, our final y value is 9 meters, and the initial y value was 0, divided by the final time value, which is 3 seconds, divided by the initial time value, which is 0. 9 minus 0 is 9, and 3 minus 0 is 3. And we have 9 meters divided by 3 seconds, which gives us a slope of 3 meters per second. And that is the speed of the object during that time interval. Now, to find the speed of the object from 3 to 5 seconds, well, this slope, I don't think we need to calculate. It's 0. It's not sloped at all. So the object is not moving during this time period. From 5 to 6 seconds, though, we can determine the speed of this object, again, by finding our final and initial y and x values. In this case, our final y value is 3 meters minus our original y value, which is 9. And our final time value is 6 seconds minus our initial time value, which is 5. Well, 3 minus 9 divided by 6 minus 1 will give you a negative 6 meters divided by 1 second, or a negative 6 meters per second. It should be obvious then that when the slope is downward, we have a negative slope, which means we have a negative velocity, which means that we're heading in the negative direction, which means that we have a negative displacement. In other words, we're heading back to where we started. And for this segment, from 6 to 7 seconds, well, I'll label this interval, and from 6 to 7 seconds, we can then see that we go from 3 meters to 0 in a time period of 1 second, which would mean that we have a speed, or a velocity rather, of negative 3 meters per second. Again, we're still heading in the negative direction. So we have a positive slope on this side, which means we have a positive velocity. We're going in the positive direction. Because remember, velocity and displacement are vector quantities that depend on direction. From 3 seconds to 5 seconds, we're not moving at all. Our slope is 0, so we have 0 velocity. And from 5 to 6 seconds and 6 to 7 seconds, we're moving in the negative direction, which means we have a negative slope, which means we have a negative velocity during those intervals. Negative slope, negative velocity. Now, because the slope of a displacement versus time graph indicates the speed of the object, it should make sense that the greater the slope, the faster the object is moving, because it's changing its displacement greater over the same period of time. So for a slope that is lower, you can assume immediately that that object is moving slower than the object whose slope on a displacement versus time curve is greater. Remember, slope on a displacement versus time curve is the velocity of the object, so the steeper the slope, the faster the object is moving. In this next section, we'll discuss how you can represent the same motion of an object using a different graph. For example, take a look at the graph of displacement versus time that we just analyzed and a graph of velocity versus time that's next to it. How do the motions they represent compare? Well, let's take a look at what happens to our y values as time goes on. In the displacements versus time graph, you can see that as time goes on, in this first segment, we increase our displacement, which means we're moving. In this graph, during the first 3 seconds, it appears as though our velocity is a constant 3 meters per second, which means we're moving as well. From 3 to 5 seconds, as time goes on, it appears as though our displacement does not change. In other words, we're not moving. And in this graph, from 3 to 5 seconds, it appears as though our velocity is a constant 0 meters per second. We're also not moving. If you can't tell by now, these two graphs are representing the same exact motion. You can see that in this first segment from 0 to 3 seconds, we have a positive velocity, and it appears over here from 0 to 3 seconds, we also have a positive velocity. From 3 to 5 seconds, it appears as though we're not moving, so our velocity is 0. And in this graph from 3 to 5 seconds, our velocity is a constant 0. Again, we can just look directly at the y-axis to see what the value is for our velocity. In the segment from 5 to 6 seconds, it appears as though we have a negative velocity, and that's a pretty steep curve, which means that it's a higher velocity. And from 5 to 6 seconds over here, we can see that we're moving at a velocity of negative 6 meters per second, just the value that we found for the velocity in this interval. And in the last 6 to 7 second interval, we see that we're still moving in the negative direction, but not as fast. We are a negative 3 meters per second for this entire last second, which is the exact same thing that we have on the distance versus time graph. So different graphs can represent the same motion, and that's okay. They just place an emphasis on different quantities. For example, with the displacement versus time graph, it's emphasizing displacement change over time. And with the velocity versus time graph, it's emphasizing the velocity change over time. Now, we've already learned that the slope of a displacement versus time graph, the slope of a d versus t graph, represents the velocity of an object. So, does the slope of a velocity versus time graph have any significance itself? Well, again, the slope of an object is equal to the change in the y value divided by the change in the x value. And for a velocity versus time graph, that is the change in our y value, velocity, divided by the change in our x value, which is time. And when you have change in velocity over time, that should look familiar because it represents the acceleration of the object over that time period. Does this make sense for our graph of velocity versus time? Well, in each segment, the slope of the graph is 0. Here, here, there, and there. So if velocity is constant, doesn't that mean that we have a constant acceleration of 0 meters per second squared? Yeah. In each segment, the slope of my velocity versus time graph represents the acceleration. Because again, my y divided by my x, or my velocity divided by my time, is acceleration. And in each one of these cases, because there is no slope, then I can assume that my acceleration is 0. It's constant, and it's 0. The slope during each one of these segments of a velocity versus time graph. Okay, so what about the area under a v versus t curve? Up until this point, we've only talked about the significance of a slope. Well, a velocity versus time graph is actually pretty special because not only does its slope have significance, but it turns out that the area under its curve represents something as well. If you remember, the equation for area is side times side. Well, in this case, we have velocity on this axis and time on that axis. So the area under this curve is really units of velocity multiplied by units of time. And when we have velocity multiplied by time, we end up getting displacement. Looking at the kinematic equations for velocity, displacement, and time, you should be able to see that if velocity equals displacement divided by time, then if you multiply both sides by time, you end up getting an expression that looks like this, where velocity multiplied by time is equal to displacement. In other words, if you would like to determine the total displacement of an object on velocity versus time graph, you need only to analyze the area under the curve. But it's important to be mindful of positive and negative areas in order to determine the net displacement of an object. For example, from 0 to 3 seconds, the area under this curve is 3 meters per second multiplied by 3 seconds. In other words, the area of this has a magnitude of 9 meters. And it's a positive 9 meters, so our displacement is going to be positive. It is above the 0 axis. From 5 to 7 seconds, it appears as though we have two areas that we can combine. From 5 to 6, that's 1 second multiplied by a velocity of negative 6 meters per second, which means that side times side is going to give us a negative 6 meters of displacement for this section. And for the section next to it, we again have a change in time of 1 second, but now we have a change in velocity of negative 3 meters per second. And side times side will be negative 3 times 1, which will give us a negative 3 meters. And if you look at the net displacement for an object that returns back to the starting point, if I have a negative 6 and a negative 3, that's a total of negative 9 meters. And you should see that that perfectly balances out the positive 9 meters that we had in the first place. This is a case of an object that returns back to its original position, just like we saw in that displacement versus time graph. It's also important to note that by looking at a graph, you can usually readily determine what's constant and what's changing. From the previous graph of displacement versus time, we saw that as time went on, first displacement increased, then it stayed constant, and then it decreased. Notice, though, that from 0 to 3 seconds, the displacement increased at a constant rate, which meant that our slope was constant. And if the slope on a displacement versus time graph represents velocity, then that would mean that our velocity is constant from 0 to 3. So, although we're talking about something that's changing, in this case, the displacement of the object, what's constant from 0 to 3 seconds is the slope, or the velocity of the object. So we're changing displacement with a constant velocity. In fact, during each one of these intervals, the velocity of the object is always constant. Here it's constant and positive. Here it's constant but 0. Here it's constant and it's negative and constant there as well. We saw the same properties from the velocity versus time graph for the same motion, except here the slope represented the acceleration of the object, which was 0 at each point in time. And the area under the curve represented the total displacement of the object. What would a graph of acceleration versus time look like for this motion? Well, if the velocity is always constant, then you never accelerate. And if you never accelerate, I guess you would have an acceleration of 0 meters per second squared the entire time. So as time goes on, my acceleration stays constant and 0. Yeah, because in each one of these cases, the acceleration of the object was 0 because the slope of this graph was 0, or from the displacement versus time graph, it showed a constant slope for the velocity being constant. Well, what if velocity wasn't constant? When objects accelerate, we know that their velocities change. We've seen this guy before. And if an object's velocity changes, then its graph of displacement versus time must no longer have a constant slope because the velocity is no longer constant. What a constant velocity looks like has a graph of displacement versus time that looks linear. But if that velocity is always changing, then you no longer have a constant rise over a run. Therefore, the graph of velocity versus time for an accelerating object would have a slope that is no longer zero. What would that look like? Well, for a graph of displacement versus time, let's analyze the following. Here, from 0 to 3 seconds, the distance the object covers gets greater and greater. In the first second, we can see that it's only moved about 0.75 meters. In the next second, it appears to move about 1.25 meters. And in the next second, it moves even more. As time goes on, the distances that I cover become greater and greater and greater. During this section of a displacement versus time graph, I am accelerating. Because the slope of my graph is always changing, I end up getting a parabolic shape. In fact, whenever you see a parabola on a displacement versus time graph, that is a clear indication that the object is accelerating. During the interval of 0 to 3 seconds, you should see that it's getting faster and faster. Therefore, its velocity is changing in a positive way, so it must have a positive acceleration. In this case, getting faster and faster. From 3 to 6 seconds, the distance still increases, but at a regular rate, so the velocity during this time period must be constant. And as a result, if my velocity is constant, then I no longer have an acceleration, and my acceleration must be zero. By looking at this segment and seeing that constant slope, I can realize that the velocity is constant, and therefore I am not accelerating. From 6 to 8 seconds, the slope of this displacement versus time graph is zero, which means that the object does not move at all, which means that both its velocity and its acceleration are both zero. If I'm not moving, my velocity equals zero, and if my velocity equals zero and it's not changing, then that must mean that my acceleration is also zero, because acceleration is the change in velocity over time. And finally, from 8 to 10 seconds, as time goes on, the displacement gets closer and closer and closer to zero as it returns back to where it started. But the distance between each second is changing between each second, because I'm getting closer and closer to my house or my starting position even quicker. Therefore, its velocity is changing negatively, and it must experience a negative acceleration during this interval. And then from 10 to 11 seconds, it appears my displacement is not changing at all, and I'm back to where I started. My velocity is once again zero, as is my acceleration. What would the graphs for velocity and acceleration look like for this kind of motion? Well, as you can see, what I've done here is I've taken my displacement versus time graphs, and I've laid below them an example of a velocity versus time graph and an acceleration versus time graph for the same motion during the same intervals. Analyzing the velocity versus time graph, for my displacement versus time, as I go from 0 to 3 seconds, my velocity is constantly changing. And as a result, on my velocity versus time graph, as time goes on, my velocity increases from 0 to 3 seconds. During the interval of 3 to 6 seconds, my displacement increases at a constant rate, which means that my velocity must be constant. And in this case, you can see that my velocity is a constant 1 meter per second. From 6 to 8 seconds, however, my displacement is not changing, and as a result, my velocity is zero. I'm no longer moving. But now, as I head back to my starting position, my velocity, which is the slope of my distance versus time graph, is changing greater and greater till I get back home. Rather, my velocity is it starts out high and then it ends at zero to where I'm not moving. And as you can see here, I start out with a high magnitude of a velocity. Even though it is negative, the negative just indicates the direction that I'm moving in. It still has a high value for the magnitude of its velocity. And that magnitude gets less and less and less until I return back to my starting position and I'm no longer moving. Analyzing the displacement versus time graph with the acceleration versus time, In each one of these cases, I can analyze the acceleration. From 0 to 3 seconds, I'm getting faster and faster, but my acceleration stays constant. From 3 to 6 seconds, I'm moving at a constant speed, which means that my acceleration is 0. From 6 to 8 seconds, I am not moving any longer, which means that my acceleration is still 0. From 8 to 10 seconds, I slam on the brakes and I return in the opposite direction. I'm still moving at a high speed, but I get slower and slower and slower until I come to a stop. My acceleration in this case is constant and in the negative direction. And then from 10 to 11 seconds, well, I'm not moving, which means that my acceleration has a value of 0. In each one of these cases, I can look at what my graph is doing and then realize, in this case, my velocity is increasing as time goes on. I must be accelerating. Remember, the slope of a graph of velocity versus time represents acceleration. So my acceleration is something during this first interval. And you can see that my acceleration is constant. And during the second interval, I'm moving at a constant velocity, which means that my acceleration should be 0. In the next interval, I'm not moving at all, which means my acceleration should still be 0. In the very next interval, I go from a large negative velocity to a velocity of 0, which means I have a negative acceleration. And in the very last step, I'm not moving at all, which means I have an acceleration of 0 once again. We should know by now that for any displacement versus time graph, the velocity of an object can be determined by simply calculating the slope of that graph. But if an object is accelerating, the velocity is always changing. So the slope must be changing as well. If the slope isn't constant, how can we determine the average or instantaneous velocities of an object on a displacement versus time graph? Let's analyze this graph of displacement versus time. As time goes on, my displacement seems to change. And from this segment to this segment, it appears as though I'm slowing down to a stop and approaching not moving at all. And then I speed back up to get faster and faster. In both of these segments, I'm accelerating. This appears to be me slowing down. This appears to be me speeding up. I would like to find the average speed of this because my velocity is changing, but I can find the average speed. Remember, average velocity or speed is equal to how far have you gone divided by how long it's taken. So in order to find the average velocity of the object, you would simply need to determine the slope of the line that connects the beginning and end points of the graph. And as you see for this graph, when we connect those points, we end up getting a graph, a line rather, that goes from the beginning to the end. And if we use the point slope method by determining points along that line that lie on the axis grid lines, then you can find the slope of this green line that connects the beginning and the end points, and that will be your average velocity. Again, how far did you go and how long did it take? That's all that this average velocity is trying to determine. However, for the same graph of distance versus time or displacement versus time, if you wish to find the instantaneous velocity, that is the velocity at any point in time along this track, you must determine the slope of the line that is tangent to the curve at that point. And what we mean by tangent is a line that only touches that curve at one point and one point only. And if you can find the slope of this line, the line that is tangent to the point that you're trying to find the instantaneous velocity of, then the slope of that line will represent the instantaneous velocity at that point. And this should make sense because as you go along this curve, the slope of the line, which is displacement divided by time, velocity, is constantly changing. In this case, it's a positive velocity because it's pointed upward, and here it appears to be about level or velocity of 0, and then it will start to point upward as the object speeds up again. But because my tangent line is always changing, then my velocity is also changing as well. Again, another indication that the object is accelerating. So again, if I would like to determine the instantaneous velocity, the speed of the object at a particular point in time, all I have to do is draw a line that only touches that point one place, a tangent line. And then I can find the slope of this line by using the point slope method. Again, those points of intersection, and take the y values and the x values to determine the slope of that line. So finding the instantaneous or average velocity of an object on a displacement versus time graph that's constantly changing can be a little difficult, and you have to find the slope of this line. However, when you have a graph of velocity versus time, finding the instantaneous velocity at any point in time is way easier. Just follow your finger at any point in time on this graph over to the y-axis, and you can determine what the value for that velocity is at that moment in time. For example, at 2 seconds into this trip, I can run my finger over, and it appears as though I'm somewhere between a half and 1 meter per second. At 5 seconds into my trip, I run my finger over, and I am moving at a constant 1 meter per second. At 7 seconds into my trip, I run my finger over, and I see that my velocity is 0, or I'm not moving at all. 9 seconds into my trip, I run my finger over, and I see that I'm moving at about -1 meters per second, or back in the opposite direction. And at the end of the 11th second of my trip, my velocity is 0 once again, as I'm no longer moving. All right, we've already seen that the slope of a displacement versus time graph represents the velocity of an object, and that the slope of a velocity versus time graph represents the acceleration of an object, while the area under a velocity versus time graph represents the object's displacement. So, slope of a displacement versus time graph represents velocity, slope of a velocity versus time graph represents acceleration, and the area under the curve of a velocity versus time graph represents the displacement of an object. So, are there any features of an acceleration versus time graph that have significance? Well, I doubt I'd be asking the question if the answer wasn't yes. Consider the graph below of an object that accelerates at a constant rate for 3 seconds. If we analyze the area under the curve, we can find that side times side, which is equal to area, or for this graph, acceleration multiplied by time, gives us a change in velocity. That's right, it turns out that the area under an acceleration versus time graph represents the change in an object's velocity over some time period. If it's getting confusing and you feel as though you need to remember at this point, well, what does the area under this mean, or what does the slope of that mean? You should realize that you don't need to remember any of those. For example, realize that if acceleration equals change in velocity divided by time, an equation that is on your reference tables, then if I ever multiply acceleration by time, I end up getting a change in velocity. Similarly, for displacement or velocity versus time graphs, if I'm looking at the slope of one of them, say displacement divided by time, that means velocity. Or if it's velocity divided by time, that represents acceleration. Or if it's velocity times time, that represents displacement. All of these equations I can easily look up in my reference tables to see if the slope of a graph or the area under a graph has any significance. The graph of an object in free fall is actually a pretty special case. The displacement versus time, velocity versus time, and acceleration versus time graph for an object that's thrown straight up and allowed to fall freely look absolutely different from one another. Yet they all represent the exact same motion. Remember, the velocity of an object on a displacement versus time curve can be found by getting the slope of the line that's tangent. Well, for an object that's thrown up, I want you to see that this slope is going from a high slope to a less steep slope to a less steep slope to a slope of 0 as it starts out fast and comes to a stop at the apex, and then it slowly starts to gain velocity, but in the opposite direction until it hits the ground at a speed that it had when it left. And similarly, for velocity versus time graph of an object that's thrown straight up, you should notice that its initial velocity is high in magnitude and positive because it starts in the upward direction. Halfway through its trip, you see that its velocity is zero because at the apex of an object that's thrown straight up, it comes to a stop. And after it starts to slowly go in the opposite direction, velocity increases but in the negative direction so that it hits the ground with the same magnitude of velocity that it had to begin with, but in the opposite direction. Positive velocity slowing down to zero, gaining speed in the opposite direction. And of course, the acceleration versus time graph for an object that's thrown straight up and returns to the ground has a constant acceleration of 9.8 meters per second in the negative direction. This is an object that, even though it's been thrown up in the air, stops at the top, and comes back down, is accelerating the entire time in the negative direction. All right, let's wrap things up. To summarize, when interpreting a graph, you must first understand what is on your x and y axes. That will completely have different consequences for whatever quantity you're trying to determine. Then you should take a look at the plot itself and form a conclusion about what is happening to each variable. Say for a displacement versus time graph, if you have something that looks like this, as time goes on, whatever variable on my y-axis, in this case my displacement, is, well, changing positively, not constant in this case, and it's certainly not zero, and it's changing quicker and quicker, which means that I'm accelerating. So for any graph, you should always ask, whatever's on my y-axis, how is it changing, or is it changing at all as time goes on? You should also realize that the area under the curve, or the slope of the curve itself, may have significance. It could represent velocity, it could represent displacement, it could represent acceleration, but you need to use your brain to see if the slope of the area has significance itself, and use equations in your reference tables to make that determination. You can get numerical values, actual values for data, for those quantities by using the axis values that are labeled on the y and x axis, and then calculating the slope or calculating the area under the curve. Finally, you need to realize that the different motion graphs can represent the same type of motion. As we've seen with previous examples, different graphs of the same motion look completely different, yet they all can represent the exact same type of motion.